Okay, so hello, welcome back. So in this video, basically what we will do is that we will talk about basically something which is related to these NPN transistors, and we will essentially, basically what we want to do is that we want to study these circuits that contain, for example, 3 transistors or 2 transistors back to back. And sometimes, for example, you have this situation over here. You have a switch over here, and the switch is something like this. This usually goes to a resistor to the ground, and this usually goes through another resistor to the positive supply rate. And this is V of S, basically positive. This is negative, V of S negative, right? And then what happens is that this common terminal of the switch is usually given to, or you can give it to the base of the transistor, and the collector of this transistor goes through a resistor, goes to the positive supply rate, the emitter goes to negative, and then there is this point over here that you can take it and give it to the base of the transistor. And again, your emitter as always goes to ground, and then there is a resistor over here that goes to the positive supply rate. So as you can see, now what happens is that when the base of this transistor is tied to ground, of course there is no current flowing through the base of your transistor, meaning that this transistor is turned off. If you have no base current, right? If you have no base current, you have no collector current. And since you have no collector current, that means that the current basically going from this point all the way up to ground, there is no current over here, which means that basically there is no which means that the whole supply voltage that is up here, this is V of S positive, the whole supply voltage up here is essentially through this resistor, is connected to the base of this transistor, right? And when that happens, so then essentially the current goes from here through this resistor, goes to the base of the transistor, to the emitter, to the ground. Your transistor is turned on, and as a result there is collector current, and then there is going to be a current going from this point to the ground. Excuse me. There is going to be a current through this from this point to the ground, which you can call I of C of 2, for example, because if you call this Q2, for example, then this would be I of C of 2 or something like that. And then on the other hand, if this switch is tied to the positive rate, then there will be the current goes from through this resistor, goes to the base, to the emitter, to the transistor, to the ground, which means that the transistor is turned on, of course depending on the values of these resistors. The transistor is turned on, meaning that there is collector current, collector emitter current going, meaning that there is going to be, the collector current is on, meaning that the current essentially goes through this load and goes to the ground, which means that the current doesn't go this way to this transistor, and this transistor is turned off, and as a result this load over here doesn't really get any current because it's not tied to ground, right? So this kind of circuit, now I will basically make this circuit on a breadboard and hopefully show it to you. I've never actually built this circuit myself, it would be interesting to build the circuit and see how actually that works, probably measure a couple of things. But essentially that's how the circuit works theoretically. And so basically you need to be able to calculate all of these resistor values, meaning that usually you have a transistor over here with a beta, and basically you want basically what your goal basically out of making this circuit is to make sure that basically when this switch is tied to ground, and that this transistor is, I don't know, turned off or on or off, whatever that was. I said I don't remember. And when this switch is tied to the positive rail, that this transistor again is either on or off. In one of the cases, the transistor is turned on. That means that this load gets current from the supply to the ground. In the other case, basically it gets no current. This load gets no current because this transistor is switched off. Now, in order to be able to understand this circuit and do the calculations, what you need to do is basically you need to understand how this voltage over here works, meaning that I can simplify this whole circuit. And as you can see, this circuit essentially there's a transistor over here, there is a resistor over here that goes to the positive rail, and there is you can forget about this resistor over here, it's not that important. And then the base of the transistor through a resistor goes to the positive rail, the emitter goes to the ground. That's all that the circuit, this part of the circuit really is, right? So, which means that basically you can simplify this circuit by drawing it this way. I draw this resistor over here. I draw this resistor over here, and then I connect it to the base of my transistor. The collector through the same resistor goes to the positive rail, and the emitter goes to the negative rail. And that's, I'm going to call this R of B, and I'm going to call this R of C. And this is my transistor. This is V of S positive, this is V of S negative, right? Now, now I don't really need, at this point in time, I don't really have I could go up, back there and basically set this up to put this whole thing together, but then I would need to basically do some recording over there. It's not really convenient for me at this point in time. I will make sure that we will basically build some circuits together based on the theory that we will learn here. But for now we will deal only with the theory, and then later we will hopefully use this, for example, in I don't know, probably making some radios or things like that. So, or power supplies or amplifiers or something like that. So, anyway, now the way that this circuit works is that basically so you have this R of B, R of C, and you have your transistor, and the whole thing is connected to a power supply, right? Now there is a couple of things that you need to understand here to understand how the circuit works. First of all, the whole circuit, the heart of this circuit is this NPN transistor. And an NPN transistor, pretty much like I'm not very, of course, well, I'm not very proficient with PNP transistors. I've actually never talked about them before, so I don't have I would have to probably figure that out first. But about NPN transistors, these are essentially current driven devices, meaning that the current that goes through the base to the emitter to the ground, meaning that from the positive ray there is this current going through this resistor, going through the base, through the emitter, to the ground, back to the ground. So there is always in a circuit, basically there is a positive supply rate, there is a negative supply rate, and any circuit basically is going to, any sort of electronic circuit, what it essentially does is a conductive path that causes the current to flow from the positive rail of the power supply back to the negative rail of the power supply. That's basically how the whole basically business of work is done in the battery, in the power supply, and all of the business, all of the story about energy basically being converted from one form to another, and so on and so forth. But essentially you can see that your power supply, for example, over here is basically connected to this point over here. This point takes you to the ground. Again, your power supply is connected to this point over here. This point takes you to the ground, right? And of course, it doesn't matter how complicated your circuit is, as long as you have a circuit, you have a number of these conductive paths that take you from the positive rail of your power supply to the negative rail of your power supply, and it's always like that. There is no other way of doing at least when it comes to in the basics of electronics, it's always like that. There is no other way of doing electronics, because it's always about electrons. There is nothing else that we can work with, really. So so now basically this transistor, basically depending on how much current is going through your base, some amount of current is going to be going through your collector, meaning that there is this I of B over here, and there is this I of C over here, which is essentially going through this path over here, right? And there is a relationship between these two, which is I of C to I of B is equal to beta. You can also call it H of Fe, right? And you can, for different transistors, of course, the value of this beta is different. I was looking at the data sheet of a transistor. This is PN2222A or PN2222. There's two variations, and so you can see that this transistor is a normal, basically the case of the transistor or the packaging is TO92A or TO18. This is not around anymore, and there is all the kinds of information about collector base voltage, collector emitter voltage, and so on and so forth. But essentially down here, and it's always a good idea to, whenever you need to, you can essentially start reading these data sheets. In the beginning, it would be like a foreign language. You wouldn't understand them. But after a while, probably if you read if you read the data sheet a couple of times, you will understand almost everything that you need, meaning that there is really not much here to understand. There is I don't know, there is only voltage, current, and inductance and capacitance. Other than that, there is nothing else really in electronics, really. And more than that, we as I mentioned, there is not much more in electronics. So you can always understand all of these things. And there is the frequency, of course, which is something simple. But essentially you can always go through all of these things to understand them, but if you need them, But essentially you can see that down here we have the DC current gain of this transistor, which the symbol for which is H of Fe. And there is all of these figures that you get over here for these two different types of transistors, actually for four different types. You get the units over here for these values, and you can see that there is no units here because these are ratios, so you have no units there. And these are the test conditions, meaning that, for example, if you have V of C is equal to 1 volt and I of C is equal to 150 milliamp, then your beta is going to be equal to 50, right? That means that your collector current is 50 times your base current, right? Because the ratio of the collector current and the base current is beta. When your beta is equal to 50, that means that your collector current is always, 50 times your base current. Whatever your base current is, your transistor is going to magnify the base current by a factor of 50, and that would be the current that is going through the collector of your transistor, right? So that's basically what happens. Now, as you can see, you can do all different kinds of things with these transistors, meaning that, for example, you can the V of CE, meaning that the collector emitter voltage of the transistor, it can be 10 volts at different basically currents. For example, 10 volts at 0.1 milliamp, at 1 milliamp, at 10 milliamp, at 150 milliamp, at 500 milliamp, 150 milliamp, and this is 1 volt, of course, and this is what, for example, what you need in order to turn a transistor on or off, because I'll tell you why. So essentially there is this relationship between I of C and I of B in the transistor, and that's called beta. You will always get a number for beta for your particular transistor, and that's how your transistor works. Meaning that whatever the value of your beta is, you multiply it by I of B, and that gives I of C, right? Very simple. So now suppose that this circuit is running, it's working, meaning that I have connected the power supply voltage positive here, negative here, and everything is working. Now, depending on what I want to do with this circuit, I need to choose the right values of the supply voltage, the right value for these resistors, so that whatever it is that I want to do, I can get it done, right? So one thing that you can do with these, with a transistor, is to turn things on and off. Meaning that you can put the transistor over here, the emitter, you give it to the ground, right? And then you have a load over here. You connect, for example, let's say that you have a lamp over here. This lamp goes to the positive supply voltage, right? Goes to the positive supply voltage. And the other end of your lamp goes through your collector, goes through your emitter, goes to the ground. If basically these two terminals are connected, act as a closed mechanical switch, your lamp will turn on, right? So now what I can do is that I can connect this base to a resistor in order to control the current, the base current, and then I can give this to the positive supply voltage, right? Which is essentially pretty much what I have done over here, meaning that you can see that the emitter goes to the ground, the collector goes to the supply voltage through a load over here, and then the base goes through the resistor to the supply voltage, positive supply voltage. So now, suppose that you have 10 volts over here, right? You have 10 volts over here. If you have 10 volts over here, and this is a 10 volt lamp that you want to basically you want to turn on, and so that means that there has to be 10 volts across this lamp, right? So that if there has to be 10 volts across this lamp, there has to be no voltage across this PN junction, meaning that this part of the circuit you can essentially redraw it as a PN junction like this, and this goes to the ground, and this is positive V of S, right? So you have your lamp over here, you have a PN junction over here, and you have the whole thing goes to ground. Now, if basically this is a series circuit, in a series circuit, basically you know that the supply voltage has to basically, depending on how much supply voltage you have, some of this voltage is dropped on this load over here, some of this voltage is dropped across this load over here, and the sum of these two voltage drops is going to add up to the whole supply voltage, right? So that means that if you have V of S over here, whatever portion of V of S is dropped across this PN junction, that portion of V of S is not given to the load anymore, right? And over here I want the whole voltage to be given to the load, right? So what I'm going to do is that I'm going to first basically put a resistor over here, call it R of C, and I want the whole supply voltage to be dropped across R of C. So how do I do that? So I can basically apply the Ohm's law to this resistor, right? So about this resistor, V is equal to IR, and I want the voltage drop across this resistor be V of S, or 10 volts. So I write 10 volts over here, and I need some current to do that. And the resistance over here, I'm just going to say that, for example, this is, I don't know, something like, for example, 10 kilo ohms, for example. Or, I don't know, let's say 4.7 kilo ohms. Let's say this is 4.7 kilo ohms, right? So this is 4.7 kilo ohms, or I'm going to write it as, for example, 4.7 into 10 raised to the power 3 ohms, which means that basically I is going to be equal to 10 volts divided by 4.7 into 10 raised to the power 3 ohms, which is the same thing as basically 10 and 10 you can cancel out, that's 10 raised to the power 2. 1 over 4.7 is the same thing as 1 over 4.7 is the same thing as 0.212765 and so on. So I'm going to take two significant figures. I'm going to take this as basically 0.21, and this goes to the numerator. This becomes 10 raised to the power negative 2. Volt by ohm is the same thing as amp. So that is I of C, right? That is I of C. That means that basically in order for the whole supply voltage to be dropped across this resistor, depending on basically considering the value of the resistor, I need basically 0.21 into 10 raised to the power negative 2 amps to be going through this resistor, right? So I need to maintain this current over here. So that means that then I can say that basically I of C is supposed to be 0.21 into 10 raised to the power negative 2 amps. Whatever that is, doesn't really matter. Now, this current is going to be controlled by the current that goes through your base, right? And we said that there is this relationship I of C to I of B is equal to beta, and I'm going to say that basically my beta is equal to, for example, 75, right? So this ratio is equal to beta. So that means that this I of C, whatever that is that I want to get, that I want to maintain in here, is going to be 0.21 into 10 raised to the power negative 2 amps divided by I of B. I of B is, we don't know what that is, we want to calculate it, and that's equal to beta, which is equal to 75. Which means that basically I of B times 75 is the same thing as 0.21 into 10 raised to the power negative 2 amps, which means that I of B is equal to 0.21 into 10 raised to the power negative 2 amps divided by 75. And let me calculate what is 0.21. 0.21 divided by 75. That's 0.0028. That's the same thing as 0.0028 into 10 raised to the power negative 2 amps, which is the same thing as, let's say, I don't know, it's the same thing as 2.8 into 10 raised to the power negative 3 into 10 raised to the power negative 2 amps, which is the same thing as 2.8 into 10 raised to the power negative 5 amps. I don't have to understand what this current is right now. Otherwise, I would write it as a microamp, for example, meaning that I would write it as, if you want to understand, for example, what this current is, of course now you don't have to, but you can write this as 2.8, you can write it as basically 28 into 10 raised to the power negative 1, right? And so I can write it as 28 into 10 raised to the power negative 1 into 10 raised to the power negative 5 amps, which is the same thing as 28 into 10 raised to the power negative 6 amps, which is the same thing as 28 microamps. 28 microamps, we understand it, but that way, in scientific notation, it's hard to understand. I mean, it's hard for me to understand this type of thing. I mean, in electronics, usually you understand, you don't use the scientific notation. You use milliamps, microamps, kilo, for example, kilo ohm, milliohm is usually not used really. But nobody says, for example, 2.8 into 10 raised to the power negative 5 amps. You would do this if you were doing, for example, physics, completely theoretical thing. But if you were working with electronics, for example, the test equipment that you have, for example, your amp meter, your voltmeter, and all of those test equipment, they don't have this sort of thing, meaning that they don't show you these numbers as 2.8 into 10 raised to the power negative 3 for negative 5 amps, for example. They give you either milliamps or microamps or amps, or of course kiloamp doesn't exist really normally. But I mean, when it comes to doing electronics, you usually don't work with the scientific notation directly. You have to convert always whenever you have to. Anyway, so now that means that basically my I of B has to be 28 microamps. That means that my I of B has to be 28 microamps, right? Now, how do I get 28 microamps in as my base current, right? How do I do that? So now let me recap in case you got kind of lost in the midst of this whole basically calculation and everything. So basically what we did was that we found that if the whole voltage is supposed to be, if the whole supply voltage is supposed to be dropped across this load, I have to have this much of current going through my collector, right? And then we use the relationship I of C to I of B. To I of B is equal to beta. We use this relationship, and using that, we calculated that for this transistor to allow so much current to be flowing through the collector, the transistor has to be supplied with so much current going from the base through the emitter to the ground, right? So that's what we know for right now. So now the question is, how do I create this current? So to create this current, what I can do is that, of course, the current that is basically induced in this branch is controlled by this resistor over here, right? So that means that I can apply the Ohm's law V is equal to IR to this resistor here, and say that basically, and of course, the voltage over here is V of S, 10 volts. You can see that this whole thing over here, basically V of S starts from here, goes through this resistor, and goes to the ground. The only thing that you have here is this PN junction, and usually across the PN junction in the transistor, for example, from base to emitter, where the current flows. For example, from base to collector, there is no current flow, of course, so you don't have to worry about that. And since there is no current flow, there is no, I'm not really sure, I've never tested this before, I've never actually read about this before, but I'm going to say that most probably there is no voltage drop, or at least very, very, very little between the collector and the base of a transistor. We will have to probably measure this and see what happens there. Of course, and there is one thing that needs to be understood, and that is basically a transistor is a device that the voltages that you measure in a live circuit, you can never say that with absolute certainty that the next time that I put the circuit together, I'm going to have the exact same readings, because the circuit, depending on what it's doing, the voltages change all the time, and it's a little bit hard to figure out how these devices. There is a whole bunch of ways that you can basically use transistors. So, but essentially you have to start with this simple, the simple calculation here, and then find your way through the whole thing, basically, right? So essentially now over here, I know that basically from base to emitter there is current flow, and there is 0.7 volts voltage drop across this PN junction. But since your basically supply voltage is 10 volts, this is no problem, and as a result, basically this supply voltage is going to, it's not important. The 0.7 voltage drop is not really important, and you can ignore it, right? So that means that for all intents and purposes, I can say that the voltage across this resistor is 10 volts, the whole supply voltage, ignoring this drop over here. And we know that the current that is going through the base is basically this current over here, which is 28 into 10 raised to the power negative 6 amps. And the resistance over here has to be picked. We have to calculate it. So that means that your R is equal to 10 volts divided by 28 times 10 raised to the power negative 6 amps, which is the same thing as basically, this goes to the numerator, this becomes 10 raised to the power 6 times 10 raised to the power 7. And then 1 over 28 is the same thing as 1 over 28 is the same thing as 0.035, since I take it as 0.036 into 10 raised to the power 7, and of course you have volts by amps, which is ohm, right? So that is R of B. That is the value of R of B. So if you 3 decimal places there, so 4, that's 360 kilo ohms basically. That's 360 kilo ohms. That's 360,000 ohms, which is the same thing as 360 kilo ohms. I don't know if this resistor is in range, but essentially that's the kind of resistor that you need to have here. So that now let me recap here. So essentially what we wanted to do here was that basically we wanted to, using this circuit, we wanted to make sure that the whole supply voltage is basically given to this load over here. This is our load basically. And the way that we did that, first we applied the Ohm's law to this resistor. So we said that if the whole supply voltage is supposed to be dropped over here, let me erase all of these things. 360 kilo ohms, right? R of B is equal to 360 kilo ohms. Okay. So we said that basically applying the Ohm's law to this resistor, we said that we want the voltage drop across this resistor to be the supply voltage, and the supply voltage, actually we are working with this circuit, right? So this is the load, and we said that then the supply voltage is essentially 10 volts. So I calculated 10, I set this equal to 10 volts, and then basically for that you need a current, and the resistance of this resistor is 4.7 kilo ohm. And then using this relationship, basically you will calculate basically I of C is equal to this current over here, right? So that basically tells me that this current has to go through your collector, so that the whole voltage is dropped across the load basically, and no voltage is dropped here, right? And that basically shows us that there is this voltage over here that I can call V of C, and in this case you can say that basically V of C is actually equal to 0 volts. That is important. That's what I wanted to show in this video. That in this case, when you make sure that the whole voltage is dropped across this resistor, that this V of C over here is equal to 0, right? With respect to the ground, of course, right? Now, so then basically we calculated the collector current. So now then we said that then in order to create that current over here, we need to get this transistor in order to basically allow this type of current to flow through the collector emitter junction. And in order to do that, there is this relationship I of C to I of B is equal to beta. We said that the beta of the transistor, the DC current gain, is equal to 75, which means that then I have the collector current and I have the beta, so that way I can calculate I of B, and that turns out to be 28 microamps. So then now I know that 28 microamps has to be flowing through your base, through the base. Now, how do I do that? I mean, how can I make sure that there is 28 microamps flowing through this branch? I put a resistor over here, and depending on the value of my resistor and the supply voltage, using simple Ohm's law tells me that if there is 10 volts across this resistor, the value of the resistor has to be 360 kilo ohms, so that the current through the resistor is 28 microamps. and then the same 28 microamps would be flowing through the base, through the emitter to the ground, which essentially causes the collector current to be so much, which causes basically the whole supply voltage to be dropped across this resistor up here, which essentially causes this voltage over here, the collector voltage, to be zero. And when this voltage over here is zero, you technically can say that basically the transistor is turned on, or it is saturated, right? So that's the whole story over here about saturation or turning on a transistor. Now, this voltage that we created over here in this manner, we are going to use it in the next video in order to put a couple of transistors together, essentially make it a little bit more complicated, but it's basically, again, the same thing really. And one thing that I wanted to point out to again is something that I found by accident really. I mean, accidentally I found this while I was reading a book really. I mean, I was searching for old, so basically what I mean, my background is in electronics, is that back then when I was a kid, I started learning how to essentially only do things and repair things from my father. And he taught me quite a couple of things about telephone systems and telephones and that sort of thing. And I could essentially, well, I could repair things if there was something, if there was something faulty in a circuit, I could change it, I could replace it, and so on and so forth. But then I couldn't really, I mean, of course you need to understand the theory of electronics at least a little bit in order to be able to put a couple of components together, build something whenever you need to. And so, surprisingly enough, there is not many good books in the market that would essentially help you do that. The only book that I found that makes a little bit sense is The Art of Electronics. But then to understand the art of electronics, your base has to be already good, and then you start reading The Art of Electronics. Moreover, to read The Art of Electronics, you need a good foundation. I mean, a little bit of calculus as well. So then what I found was that there was a book called Complete Electronics Self-Teaching Guide with Projects with Harry Kybet and some gentleman by the name Boysen, if I'm not mistaken, Earl Boysen. And they have written this simple book. But then, if you already know a little bit of electronics, and if you can basically follow a simple book, then basically little by little, as you go through this book, you will essentially learn how to basically design things, because it's just a very simple thing. Meaning that when you can understand that, for example, when there is a power supply here and over here, and the current goes this way and that way and doesn't go this way and that way, that's basically design. I mean, design is nothing more than that really. And all of these necessary concepts are essentially explained in this book. Of course, then you have to spend some time and put them together in your mind and all of those things. And now, basically, I took some time and went through that book and did a couple of experiments. And now I'm just basically talking about these things on YouTube, and hopefully, I mean, if you have the time to go through these videos and if you have the and if you need to or want to understand them, then essentially these simple videos you can use as a simple course on design, and then of course whatever you learn, you have to keep doing that over and over again, basically keep trying different things, and that becomes experience, and then you become a good designer in electronics. But essentially you can use all of these videos or the same book that I mentioned in order to learn design. And of course the book, the Art of Electronics, there is good things that you can get from that book as well. But you need a good base for that. So hopefully you learned a little bit of something in this video, and then in the next video we are going to basically try the same thing using 2 transistors. I'll see you in the next video, and thank you.